Hi everyone, today I'm presenting my work on federated time-dependent GNN learning from brain connectivity data with missing time points. This work has been done at Basira Lab by myself and supervised by Dr. Islam Rekik. Given a baseline brain graph acquired at T0 time point, how to predict its evolution trajectory over time? There are several studies on brain evolution prediction with sample selection. A study has worked on brain graph prediction, proposing a learning-based atlas-to-atlas similarity estimation to predict the brain graph evolution trajectory from a single observation. The other one used tensor completion to linearly impute the missing brain connectomes in training trajectories. However, such frameworks do not preserve the graph topology due to their graph vectorization steps. Further, graph neural networks emerge as a paradigm to preserve the graph topology when learning from graphs, as our work used a graph convolutional adversarial network to learn the nonlinear mapping between time points. Also, another work proposed recurrent brain graph mapper, composed of a set of recurrent GNNs, where each GNN evolves the current brain graph onto its next time point. However, all these methods share a prime challenge. They are not designed to handle decentralized datasets with varying acquisition time points. In network neuroscience, data scarcity is a big hurdle, limiting the generalizability potential of deep learning models, which are data hungry. Federated learning came out as a promising paradigm to the data scarcity problem by collaboratively learning from decentralized datasets. In federated learning, multiple clients train their local models on their local datasets independently while benefiting from the learning of other hospitals via a central server in a fully privacy-preserving manner. Federated learning uses a central server that receives the local model weights, then aggregates them into global model weights, which are then broadcasted to the local clients. In our case, the hospitals might acquire brain connectivity data in different periods of time, causing a mismatch in acquisition time points. Therefore, for some hospitals, data might be missing at several time points. So, how do we collaboratively train a global model for each time point, benefiting from all possible data without violating data privacy? To overcome this challenge, we propose 4D FedGNN+, which is the first federated brain graph evolution prediction framework that learns from decentralized datasets with missing time points. 4D FedGNN+ uses a GNN for each time point that learns to map a brain graph onto its next time point. A GNN acts as a generator if the ground truth data is present at the next time point, or it acts as a self-encoder if the data is missing at the next time point. As an overview, each local hospital trains a GNN per time point that acts as a generator or a self-encoder based on their corresponding temporal conditions. After training a while, hospitals send their local weights to the central server, and the central server performs a mixed federation strategy. Here, we have a close look to GNN-based time-dependent prediction. A hospital might encounter 4 possible conditions when training a GNN for a time point. First, the hospital might have brain connectivity data at both time points t and t+1. Its GNN acts as a generator and uses data at time point t+1 to compute the loss. Next, it might lack the data at the next time point, leading the GNN to act as a self-encoder. The GNN computes the loss using the brain graph at time point t. In the third case, the hospital might lack the data at the current time point t. First, the hospital generates the input data using the GNNs of the prior time points and then trains the GNN using the predicted brain graph at t. Since it has available data at time point t+1, it acts as a generator and computes the loss using the ground truth data at t+1. Finally, the hospital might lack the data at both time points. As mentioned before, the hospital uses the GNNs at prior time points and generates the brain graph at time point t. Then it uses this brain graph as an input and also to compute the loss since it acts as a self-encoder. In our full loss term, to improve the quality of the predicted graph, we add an L1 loss term to topological loss based on node strength. Here is our mixed federation strategy. After the local hospitals train their local GNNs for a few rounds, they communicate and send their GNN layer weights to the central server. There are two federation methods the server can execute, and they operate in turns. So the central server executes one of the federation methods in each turn. The first federation method is GNN layer-wise weight aggregation. In this method, server averages the received GNN layer weights and generates a global model to broadcast back to the hospitals. The second federation method is pairwise GNN layer weights exchange. In this method, the central server randomly pairs the local hospitals and exchanges their weights with each other. To evaluate 4D FedGNN+, we use 113 subjects from the OSS2 longitudinal dataset. Each subject was scanned on 2 or more visits, separated by at least 1 year. We evaluated our framework using 5-fold cross-validation, where in each run, 1 fold is used for testing, while each of the remaining 4 folds serves as local hospitals. We masked 2, 3, and 4 out of 8 time points to vary the ratio of missing data. Further, we evaluated our framework using a simulated dataset composed of 120 subjects. We generate the brain graphs using the multivariate normal distribution computed by using the mean connectivity values and correlation matrices of the OSS2 dataset. Each subject has 6 time points. We selected 3 ratio values as 5, 8, and 10 out of 20 to mask out the time points. We benchmarked our framework against 2 of its variants, respectively 4D GNN, the vanilla method where hospitals train their local data without federation, 4D FedGNN, the variant where we use a single federation strategy based on GNN layer-wise weight aggregation, so non-mixed strategy. Here we can see the MAE results between the ground truth and predicted brain graphs for OSS2 dataset at T1 and T2 time points. Our proposed technique 4D FedGNN+ significantly outperformed the comparison methods 4D GNN and 4D FedGNN in all masking ratios. For more experimental results, you can check our paper. In this work, we introduced the first federated learning framework to predict time-dependent graph evolution trajectory using non-iid decentralized brain connectivity datasets with temporally varying acquisitions. We proposed a generic mixed federation strategy. Our framework significantly boosted prediction accuracy compared to the baseline methods in both real and simulated datasets. In our future work, we will work on how to better aggregate received model weights learned from non-iid longitudinal data. For more, please visit us at basira-lab.com.